We're doing some volumes of revolution, and for this video to make sense to you, you should have already become knowledgeable on the pancake method, otherwise known as the circular discs method. So likewise, I'm going to name this method after a delicious food, the donut. The calculus books would call this the washer method. Like the pancake method before, I think you'll agree the donut method is a much better description. We're only going to do one example here. The pancake method, we did 3 examples because you were learning something brand new. Now that you've kind of got your brain into gear, this is going to take fewer examples to get the point across. We have a region, and I've chosen very friendly equations, and we want to rotate this region about the x-axis. So the x-axis, you're able to grab it and go bzzz, bzzz. And this region rotates about the x-axis at blazing speeds, so fast that this whole region becomes a blur and you can kind of see a 3-dimensional figure. If you didn't see it when I accidentally uncovered it, and I hope you didn't, you should take a moment to pause the video and see if you can't sketch it or imagine that region. I have a feeling you could even see it through the paper, but there is that region. So as this thing rotates around the x-axis, what you end up with is what looks like a cylinder or a can of soup, but this region in here is empty, which means the center of the can of soup is empty, but empty in a weird conical-like way. So there's my best attempt at a 3-dimensional figure of this, but here's your dilemma. Earlier in the pancake method, we said, hey, you got to cut a slice through that region. And in this case, that slice would have to go way down here because this thing is rotating about the x-axis. So if I were to recreate that slice over here, that slice would look like that. Or 3-dimensionally, it would look like that. Well, here's something different about this method. If you pull that slice out of that figure, you are holding a circle, but that circle has a lot of empty space on the inside. You could hold it in front of your eyeballs and you could look right through it. So what you have is kind of a very flattened donut, which is why I call it the donut method, but calculus people call it the washer method because a washer is a flattened circle with space open in the center. So we have to basically accumulate the area of a bunch of these things. So informally, I would say beginning slice to ending slice, the area of a bunch of those donut slices. Remember that your very first slice in this case would be here at x equals 0. Your last slice would be here. What would that x value be? Looks like it would be a 4, but I reserve the right to change my mind on that later. Yeah, that is going to be a 4. And what I'm going to do is for any one of those individual slices that you see, I have to compute the area. Well, let's go back to your geometry days for a second. We're currently taking a break from the real problem to go back to your geometry days. In geometry, you learned how to find the area of a circle, and you were quickly bored because it was pretty easy. Then your teacher gave you this problem, which was find the area of the speckled region, which is kind of like a circle, but you're missing this inner piece. So then, because you're smart and you love math, you eventually figured out it's a pi r squared minus a pi r squared, meaning the whole big donut minus the little baby donut in the center. Sorry, I'm going to restate that. The whole big circle minus the little baby circle in the center leaves you this ring area. And if you want to see it in action, you could study that, but I think you remember this. So we're now kind of like the pancake method, going to be thinking about slices of circles, but our circles are going to be more complicated where we have to do this little geometry trick. So now we're back to the donut method problem. This area, or region, turns into this three-dimensional figure. This slice is a circle with a hole cut out of it. So we're going to do the accumulation, or the integral, from beginning to end of the pi r squared minus a pi r squared, because that was the geometry trick. Remember, we chose dx because we are going to be slicing circles as we travel along the x-axis. I'm going to do a calculus property. You don't have to do this, but since pi is common to both terms, I could factor the pi out here and just call it r squared minus r squared with a pi here. That means the pi can go there. So I'm going to do this because it's going to make my work seem a little easier and less prone to error. Just a side note, this thing is not that. It's going to be tempting to write that, but that is not that. They just look similar, but they're not the same. All right, so now we need to figure out our radius. And this is where the radius again becomes a little bit of your enemy. If you think about that circular slice, you have a hole in the center. You end up with a little r and a big R. In terms of this, there's holes in this thing. There's my little r, and then my big R, I'm going to draw it off to the side. There's my big R. In terms of this, there's my little r. There's my big R. So you got to be pretty organized. And check this out. The little r and the big R, those are both regular old y values. They're not even y-like. It's a distance from the x-axis up to the function. It's a distance from the x-axis up to the other function. So I'm able to replace the big R and the little r with y values, and I don't even need to do any trickery for y-like values. So then finally, I say, well, that big y value, I'm not allowed to use y because it's a dx problem, but in this case, y is the same thing as 6. Oops. Y is the same thing as 6. And then the little y, which is this piece right here, y is the same thing as x plus 2. So little y can be replaced with x plus 2. You very well may stop there, or you could turn it into a final answer. Now keep in mind, this problem could have been made even more difficult if these radius, little r and big R, were not regular y values, because sometimes they could be y-like values or x-like values. But those are things you learned when you were learning the pancake method. You would just have to roll with it in the donut method. In almost all of these methods, your radius and your ability to draw your radius on your pictures is probably the key to your success. You have one more method to go for volumes, and that will be the mashed potatoes method. That also was foreshadowing.